Okay, so our essential question today is how is the life cycle of a star, such as the sun, similar to the cycle of life on Earth? There is a star article that I would also like you to read. Um, you can do it before or after the notes. Oh, okay, this is learning target 25. Be able to explain a life cycle of any size star. Okay, so if we look at stars, they shine. Well, the reason why they shine is because of nuclear fusion. Pretty much two hydrogen atoms combine to make helium. When this happens, it releases a tremendous amount of helium or energy. So this is how stars shine by nuclear fusion. So two hydrogen atoms fuse together, release a tremendous amount of energy, and that gives the star helium. When a star runs out of hydrogen to combine, then it starts to die. Okay, so how is a star born? A star begins as a large cloud of gas and dust called a nebula. Pretty much inside that nebula, if you look at this picture, there's all different types of stars in there that are forming right now. Um, Basically, when enough of that gas and dust has enough mass, the force of gravity will cause the matter to contract and come together, and then those smaller pieces eventually become a star. Okay, so we're going to watch a short little video that is a artist's impression of flying through a nebula. A lot of gas and dust. You can see individual stars already forming. Yep, that was it. One more time. So a collection of dust and gas contracts due to the force of gravity, and you have stars forming. So a lot of stars form inside a nebula. Okay, so most stars, if we look at the life cycle of a star, exist in the main sequence. About 90% of all the stars in the universe are main sequence stars. Two of the scientists who discovered this relationship was Hertzberg and Russell. They developed a graph to show the relationship between temperature and brightness of the star. Okay, so let's take a look and see what that looks like. Next one. Okay, so this red line right here is the main sequence. So most stars, the brighter they are, that's luminosity, the hotter they are. Okay, and that's why you get this best line fit for main sequence stars. You can see that the temperature is reversed. The hotter temperatures are down to the left, cooler temperatures down here. So the brighter, the hotter they are. As the stars start to cool in temperature, they're not as bright. Okay, now some stars do not exist on the main sequence stars, and that's about 10% of the stars in our universe. If you look over here, you can play around with the temperature. Okay, if I decrease the temperature but keep the brightness the same, I move along this way. Okay, I can do the opposite. Okay, I can decrease temperature. Okay, and notice how big the star is. Large mass stars you would think would be the brightest ones, but they actually burn the fastest, and they don't live very long. Okay, so let's take a look at the life cycle of a star. So all stars start out as a nebula. And we're going to start first with an average sized star. An average sized star, like our sun, will exist for most of its life in kind of this stage right here. It's burning hydrogen, turning it into helium, creating that energy. When the star starts to run out of hydrogen, okay, it turns into a red giant. Basically, what happens there, and we'll go into a little bit more, is the star loses its outer atmosphere. Outer layers of the star start to expand. Then you have, I kind of ignore this, but some people say you have a little planetary nebula But I usually say we go from a red dwarf to a white dwarf, which is basically all the mass that's left over in the star condenses to a small point and it will eventually stop giving off light. Now, really massive stars, okay, they have a shorter life cycle, and you would think that average stars would, because they have less hydrogen to burn, they wouldn't last as long. But larger stars burn through their hydrogen a lot faster. It's kind of like if you think of a gambler. A gambler who has a lot of money is going to bet large, and he has a greater chance of losing his money quickly. Whereas someone who doesn't have as much money to lose might be very cautious in their betting, and so they actually stay alive a little bit longer as far as the gambling goes. That's kind of the same thing with stars. So larger stars burn through their hydrogen fuel a lot faster than average stars, so they don't live as long. When they start to lose their outer layers, they turn into a super red giant, and then once they've lost their outer layers, what's left of that massive star condenses to a single point and creates a huge explosion called a supernova. Now, depending on the size of the star, they will either become a neutron star or a black hole. And we're going to go into those in just a minute. Okay, so if we take a look at our main sequence graph again, what you're going to see is, again, most of the life cycle of a star is spent in the main sequence. When they start to change into giants and supergiants, because they are emitting a lot of energy, that energy is escaping into space, they're really bright. But they're not very hot because a lot of that energy is getting released into space. Then when you've got the white dwarfs, they are really hot because all that matter has collapsed to a single point. So that increases the pressure, so temperature goes up. But they're not as bright because nuclear fusion is no longer going on. So that's why you've got some stars that don't fall in the main sequence. Most of the life of a star is spent in the main sequence. And then when they start to die, they will turn into giants and supergiants and then the white dwarfs for average stars. So, and then one thing I want to point out to you when you're looking at this graph, really hot stars are blue. Really cool stars are red. So it's kind of opposite of what we think. We always think is red is really hot, but actually when you look at a fire, the blue part of the fire is even hotter. So stars that are blue are hotter than stars that are red. Okay. So let's go back, and you're going to want to make sure you draw this life cycle in your notes so that you know, because that's our target. We've got to be able to look at an average size star, and you should be able to tell me what it turns into, a larger star, what it will turn into, and explain those steps. So let's go into the different parts. So a red giant. So the star has run out of hydrogen to nuclear fuse into helium release energy. So there used to exist a balance between the pressure that came from the hydrogen core and gravity. So remember when we talked about forces and we talked about balanced and unbalanced forces? So if you've got the core of a star is exerting the force of pressure because that force comes from nuclear fusion. So when the star is fusing those hydrogen atoms and releasing energy, that creates pressure that pushes this way. Now, the opposite direction, and I wonder if I can get this in a different color, is the force of gravity. So the force of gravity is coming in this way, trying to pull that matter to the point. Well, as long as there is a balance between the force of pressure that a star exerts from nuclear fusion and the force of gravity, then a star is balanced. That means it's staying very, very stable, which our star right now is doing, our sun. However, eventually what will happen is when the hydrogen core is starting to become depleted, then what happens is that force of pressure becomes less. So it decreases. And when that decreases, the force of gravity takes over and we have an unbalanced force. because the force of gravity is now stronger, and so it's going to exert a lot stronger force. It's going to be thicker, okay, and it's going to start pulling the star down to the center, all the mass to the center. Now, what happens is when this occurs, when you have those unbalanced force and gravity is taking over, the core is going to start to contract because the force of gravity is pulling everything to the center. But temperature starts to increase because the outer layers expand and cool. And the reason why those outer layers expand is because lighter elements leave the star. They escape the force of gravity. So that's why the red giant is expanding. Those lighter elements, like hydrogen and helium, are escaping out into space. And guess where that hydrogen and helium goes? It goes to nebulas. Then we have a white dwarf. A white dwarf, after the helium has been used up, there's no more helium. Okay, outer layers have already escaped, leaves behind a very hot, dense core. Remember, the force of gravity has pulled the rest of the matter left to a center core that's under immense pressure, so it's pretty hot. It will eventually cool, though, because there's no longer nuclear fusion occurring, and it will stop giving off light, because remember, nuclear fusion is what creates the light. And when this happens, the stars will be about the size of Earth. Okay, now really large stars turn into supergiants. So the core heats up to higher temperatures, heavier elements start to form through fusion, and iron forms in the core. Iron cannot release energy through fusion, so the core collapses, and when it does that, release a shock wave called a supernova. So pretty much what happens is when a star runs out of hydrogen, it starts to try to fuse other elements together to create energy because the star does not want to collapse. So in really large stars, they try to get heavier elements like carbon to fuse together. And they do that for a while. That's why they increase to higher temperatures. But eventually when that stops, because they run out of the carbon, they're left with just iron. Iron cannot fuse and release enough energy. So that's when the core collapses due to the force of gravity, because remember, that pressure that goes against the force of gravity is no longer there from nuclear fusion. And you have a shock wave called a supernova. And then supergiants can either turn into neutron stars or black holes. Neutron stars are very dense, okay, and pretty much what happens is when matter coalesces to that core. Remember, electrons are on the outside of the atom. Because gravity is so strong, it actually pulls those electrons to the center of the atom, the nucleus. So an electron actually turns into a neutron, so that's why we call them neutron stars. Black holes are even more dense. So this is an even larger star, and all the core's mass collapse to a single point. Gravity is so strong that nothing can escape, not even light. And stars and planets will orbit black holes. At the center of every galaxy, which is a collection of stars, solar systems, is usually a black hole. And that's what our star, our solar system, rotates around. Now, this website is also on the website. You can go to it. It's a little interactive website that lets you learn a little bit more about black holes. There it goes.
Are out there. But what are they? The mass of the Earth creates the gravity that pulls things to the ground. With enough power, we can escape that gravity and leave the Earth behind. But if you could take the Earth and squeeze it to the size of a marble, the gravity on the surface would be much greater. Not even a beam of light could escape. We call this a black hole. Fortunately, neither the Earth nor the Sun will ever become a black hole.
Only stars can become
But
black
black
holes.
holes do exist. Can you find one? Explore it. And understand it. Black holes. Gravity's relentless pull.
Okay, so you can go to this website and you can actually journey to a black hole. Okay, gives you a little bit more information than what I gave you in the notes. And it kind of takes you through different interactions that you can do. So this is kind of what it looks like, and you can actually try to go around and find black holes. So if you'd like to look at this, link is on my website. Okay, so the last thing we're going to talk about, of course, is the theory of conservation of matter. So stars form from matter released by other stars. So when stars are dying and they turn into those red giants, they're releasing all their outer layers of the star. So all that matter is getting released into space. So stars eject enormous amounts of matter. And that enormous amount of matter collects and forms nebulas, which then in turn creates new stars and planets. So stars cannot be created or destroyed. We can only change the matter. So in kind of, I don't know if you've heard the saying before, but you guys are all made up of stardust. That's because everything in the universe, stars, solar systems, and black holes, were created by the stars going through their life cycle. So a star starts out as forming from a nebula. After it starts to die and releases all its matter, that matter that it releases turns into a new nebula where new stars and solar systems can form. So you guys are all made up of stardust. All right, so hopefully we've got a better understanding of a life cycle of a star, how it is born, the stages that it will go to based on its mass, and you will be able to explain the different stages.